So let's go ahead and look at question number 12 here now. Okay. So question number 12, we've got a man launches his boat from point A on a bank of a straight and still river that's 3 kilometers wide and wants to reach a point B 8 kilometers downstream on the opposite bank. He can row at a certain rate and he can run at a certain rate. Where should he land in order to get to point B as quickly as possible? So let's look at this problem real quick. Let's look at the picture that goes with this. So we've got a straight and still river that's 3 kilometers across. Pretty wide river, maybe the Mississippi at some point. And we've got some point B that's down 8 kilometers downstream from the start point of point A. Oh, that's easy enough. Okay. So what's the deal here? Well, this person can row across the stream and then run the rest of the way to point B. Okay. Hopefully you see that if the person is an extremely slow rower and an extremely fast runner, they would probably want to just row straight across the stream, or very, very close. You would never go straight across, but very close to straight across, and then spend the rest of the time running. And if the person was a much faster rower than they were a runner, then they would want to just cut the corner and spend all the time rowing. But depending on how close these two rates are to each other, there's some sweet spot that the person should aim for in order to minimize the amount of time they spend traveling. Okay. Now, this is sort of a silly problem in that, well, 2 things. Let me first say, though, that the amount of time it takes to compute this problem negates any option that you would take. So in spending the time to compute this problem, you're going to lose out. Okay? So you might as well just aim and go if you were this person. I'm not claiming that. Okay? The next thing is, they actually did some studies, and your textbook has an interesting anecdote about this. Okay? So for those of you interested in animal biology or animal behavior, okay, they did some studies and found that dogs naturally do this. If you got a dog and you throw a ball into the water of a lake or something, the dog will naturally run along the lake for a certain amount of time before jumping in and swimming diagonally towards the ball. And if you were to average out over the long run, on average, they're landing always at the sweet spot. Now, not every single time they do that, but on average, they average hitting that sweet spot. So your dogs are better at calculus than you are. I'm sorry. But that's an interesting fact. How do the dogs know that? Yeah. All right. Well, I mean, yeah, so you make the argument that the dogs that are able to do that survive, and the dogs that aren't able to do that don't survive. So over time, you select for it. Okay. What's that?
I was saying the whole, like, my dog ate my homework. They're just making sure we don't become smarter than them.
Keeping you down, huh?
Yep. That's why I don't have a dog.
All right. The other thing is I would argue that this is actually, in one way, one of the most important calculus questions we do, in that billions of people rely on this calculus question every single day. They're just not doing the calculus. Where do we use this question every single day? GPS, Google Maps, route selection is done with this optimization procedure. Of course, it's far more complicated because there are many, many routes from point A to point B, and there are often many, many turns that have to be done along point A to point B. But it is one giant optimization problem where on road A, if you go, this road allows you to go 30 miles per hour, this road allows you to go 45 miles per hour. Where should you get on to the faster route in order to get to your destination as quickly as possible? So while you can't compute that problem very quickly, it is being computed for you every day. Zachary?
Oh, that's not a question.
Oh, okay. Any questions on this problem? All right. So this is how we do it. And again, I don't know, maybe you could come up with this problem on your own, but I think it'd take you several hours to answer this question on your own. So I'm just going to show it to you. All right. The time total that you spend is equal to the time that you spend rowing plus the time that you spend running. True? Okay. Then we remember the age-old formula, the distance is equal to, no.
Distance?
Sure. Distance is equal to rate times time. Okay, that's a very old formula. We use it all the time in algebra. Let me just remind you of it. If you go 30 miles per hour for 4 hours, you will travel a distance of 120 miles. Okay? So distance is equal to rate times time, which means that time is equal to the distance over the rate. Distance over rate. Okay? Your time is equal to your distance over your rate. So that means that the time that you spend total is equal to the distance that you row over the rate that you row, plus the distance that you run over the rate that you run. So if I call this point here, and here I'm not, in this particular problem, I'm not going to do the work to come up with the constraint. To be honest, by the time you've built the objective function, plugging in the constraint's kind of silly, so we'll just do it. Okay? The constraint is that this distance right here plus this distance right here must equal what? 8. The 8 kilometers. But we will substitute in the constraint as we build this. Okay? I don't want to label this x and this y. It's just too long to do it that way. Okay, so what is the distance that you row? Based on this construct here. That's true, but I'd rather do the distance I row, I'd rather actually calculate it using x. Okay, so what can we see here? Well, because this is a straight river, we formed a right triangle, right? And this side of the right triangle is 3, and this side is x. And so we just need, the distance that you row is the hypotenuse of that right triangle, right? So the distance that you row is the square root of the sum of 3 squared plus x squared. That's the distance that you row, the hypotenuse of that triangle. Everyone okay with that? All over the rate at which you row. How fast do you row? I think we said that you row 6 kilometers per hour. Plus, then if x is the distance where you landed, how far do you have to run? So this was somebody who was given this answer earlier. How far do you have to run? You've got to run a distance of 8 minus x. To be honest, I think it's silly to take the time to call that y and then substitute in the constraint that x plus y is 8. Okay? So that's where the constraint of this problem comes in. All over the rate at which you run. How fast do you run? 8 kilometers per hour. Okay. So now we've got our time, the time total as a function of the variable x. So you tell me where you land, and I'll tell you how long it will take for you to do the whole route. So we've got, I'm just going to recopy it. T of x is the square root of 9 plus x squared all over 6 plus 8 minus x over 8. So let's find t prime of x here. Well, let's see here. That's going to be 1 over 6 times 2 times the square root of 9 plus x squared times 2x plus negative 1/8. Folks, I thought of this as 1/6 times the square root of 9 plus x squared, and I thought of this as plus 1 minus 1/8 x. Dividing that 8 into both terms on the right-hand side, so when I took the derivative, I just got minus 1/8. So we found the derivative. Now what do we need to do? Find its critical numbers. Okay? Well, it's only critical numbers. In this case, are going to come where it's 0. Okay? So we end up with, let's see here, 0 is equal to x over 6 square root of 9 plus x squared minus an 8th. Where did the 2's go? Okay, they canceled. So we get 1/8 is equal to x over 6 square root of 9 plus x squared. This is the first time we've had to solve a radical equation in a long time. Okay. I recommend the technique of cross multiplication here, although there are many other ways to do this problem. If we cross multiply, we get 6 square root of 9 plus x squared is equal to 8x. Okay? Now, I've got an equation with a square root in it, so I isolate the square root term, done, and then I raise both sides to the index of the radical. Well, this is a square root, so I'm going to square both sides of the equation. Squaring both sides of the equation gives me 36 times 9 plus x squared is equal to 64x squared. So let's see here. This gives us the parabola, a messy one. Let's see here. 36 times 9 plus 36x squared is equal to 64x squared. So this gives me 36 times 9 is equal to, subtracting over 36, 28. Right? Yeah, 28x squared. Is that right, folks? Okay. So then we get that x squared is equal to 36 times 9 over 28. So let's see here. That gives us, so folks, notice I didn't want to multiply 9 times 36 just because I'm lazy. Okay. So at this point, I'm going to go ahead and cancel out like factors. 4 goes into both those expressions. So I get 9 times 9 over 7 is equal to x squared, or 81 sevenths is equal to x squared. So we get x is equal to plus or minus the square root of 81 sevenths, or plus or minus 9 over the square root of 7 is equal to x. Okay, folks, all I did was solve this equation. I might not have done it the way you would have. All right. So we've got two critical numbers, but on the interval from 0 to, and here I'm just going to be lazy and put 0 to infinity. I'm not going to worry. Actually, no, we could go ahead and do this. What's the biggest x could be in the domain of this problem? 8. So on 0 to 8, x equals 9 over the square root of 7 is the only critical number. Okay. So I wish I may, I wish I might. What do we think this is going to be? A local what? Yeah, because we're wanting to get there in the shortest amount of time, right? Okay, so we're hoping this is a local minimum. What do we need to do to find out that it's a local minimum? I recommend doing the second derivative test on this. So let's go ahead and find, right way up here, t double prime. Aha, success. There we go. This was our first derivative. So let's find the second derivative. Okay, so we'll have to do a quotient rule here, right? So we do the bottom times the derivative of the top minus the top times the derivative of the bottom, which is just the derivative of the bottom term. So that would be 6 over 2 square root of 9 plus x squared times 2x, all divided by the bottom function squared. Okay, and I called this f. I should have called it what? What was I calling it before? Yeah, I should call those t prime and t double prime. Okay, so now we're going to look at t double prime of 9 over the square root of 7. I'll let you guys check this on your own time. What are we going to get? We're going to find that we are greater than 0, so concave up with a horizontal with a horizontal tangent line. So we found what? So x equals 9 over the square root of 7 is a local what? Min. Okay, you don't have to write this part, but I'd like to say it just to keep just feel like I'm doing my job. Okay? So by the theorem, x equals 9 over the square root of 7 is a global min. Right? How come? Because it was the only local min on 0, or was the only local extrema on 0, 8. Therefore, it's its corresponding global. Now, where the maximum then has to occur is at one of the two endpoints. Which one? You'd have to check to find out where the maximum occurred. Okay? All right, let's see if we've answered the question. I don't feel like we have. Oh, maybe we have. Where should he land in order to get to point B as quickly as possible? Well, let's see here. 9 over the square root of 7. Somebody want to give me a decimal approximation of that?
It is
3.4 what?
0.
3.40. Great, thank you. So about 3.4 kilometers downstream is where you should aim for. Of course, your dog knows that.